Hello and welcome to 10.6 Spheres. Okay, so just a little reminder, a sphere is a set of points in space that are a given distance from a given point. So this is similar to the definition of a circle, where a circle is a set of points on a plane. Remember, a sphere is in space. So here O is the center, OA is the radius, BC is a chord, DA is a diameter, EF is a tangent. Remember, a tangent line, when we talked about circles, just hits a circle in exactly one point. The same is true for a sphere. A tangent line hits a sphere in exactly one point. And then the line BC, when I extend that chord out, is a secant. So let's talk a little bit about a secant plane. A secant plane to a sphere is a plane that intersects the sphere in more than one point. So if you look carefully at the figure here, the intersection would look like I am cutting the sphere, and the plane that would remain is a circle. A tangent plane to a sphere is a plane that intersects a sphere in exactly one point. And again, that point is called the point of tangency. So instead of talking about a line to a circle, we are talking about a plane to a sphere. And it looks like this. Now, you see the right angle there from the radius to the point of tangency? A sphere, like a circle, has infinitely many radii. The difference between a circle and a sphere, circles are planar, okay, so they have infinitely many along the plane, but a sphere has infinitely many in every direction. So I can drop that perpendicular to hit the point of tangency wherever I want. So here's our first theorem, Theorem 1019. Now remember, you don't refer to theorems in proofs as their number as given in the textbook, because depending on the textbook, the numbers are different. So you need to memorize them, at least in their idea. So the intersection of a sphere and a secant plane is called a circle, which I mentioned to you in the definition of a secant plane. But here's a picture, okay? And so I can actually prove this theorem, and it is written for you on page 441 in your textbook. It has 14 steps, okay? So the given is sphere S with the center C and a secant plane, which we would call N. Okay, that would be the given, and then you have to get all the way down to the intersection of a sphere and a secant plane is called a circle. So it ends with the definition of a circle, which again, when we put together proofs, they don't have to be in this exact order. This just happens to be the shortest order. A great circle of a sphere is the intersection of the sphere and a secant plane that contains the center of the sphere. So the reason why it's called a great circle is because if you go through the center of a sphere, it's the largest circle that you can make. Much like the diameter of a circle is the largest chord in a circle, the secant that goes through the center of a sphere is the largest circle that you can make. So again, that's why it's called the great circle. 2 points on a sphere that are not on the same diameter lie exactly one great circle of the sphere. So let's look at a picture of that. So here are 2 points on a sphere that are not on the same diameter. They lie on exactly one great circle of the sphere. So let's cut that so that we're going through the center. So 3D pictures help us a lot. 2 great circles of a sphere intersect at 2 points that are endpoints of a diameter of the sphere. So here are two great circles of a sphere, and they intersect at exactly 2 points that are the endpoints of a diameter. So there's a diameter in space. Again, 3D helps us a lot here. All great circles of a sphere are congruent. So no matter where I draw my great circle, as long as I'm going through the center, they all share the same radii, which means the circles are congruent. And there are infinitely many great circles. A secant plane of a sphere is perpendicular to the line containing the center of the circle of the intersection of the sphere. A plane is tangent to a sphere if and only if it is perpendicular to the radius at that point of tangency. So let's talk about traveling on the surface of the Earth. Okay, so it's always helpful to find the shortest distance is a straight line, but on a sphere there aren't any straight lines. So there are only arcs. So we need to find the distance between A and B. You have to find the length of the arc of the great circle that contains A and B. So here is the formula for finding the distance of an arc. You're going to use the measure of AB, and we actually use the circumference of the great circle. So if you remember, the circumference equals 2 pi r, and that's where that 2 pi r is there. Okay, so we need that measure in degrees divided by 360 times the circumference, and that will give us just the piece that we need, the distance of AB. So let's do a practice real quick. Alright, so here's the same figure. I've just shrunk it up a little bit, and the formula that I mentioned before. Now let's just go ahead and have some givens. We can't find all of these things without some things given to us. So we're going to say the measure of the arc is 3 degrees. So the arc is 3 over 360. Now the circumference of the great circle, we're going to say the radius is 8 in this example. So we're going to go ahead and plug in those values first. And now we need to simplify. Now 3 over 360 simplifies to 1 over 120, and 2 times 8 is 16. So there's 120 times 16 pi. And if I put all of that in my calculator, well, I can still actually simplify it one more step by saying 2/15 pi. That's the exact answer. But if I put it in my calculator to give an approximate units, it ends up being 0.4189 units. So it's actually less than half a unit, depending on if this is miles, feet, we don't know. Now for your WSQ summary, I've just given you 2 practice problems to email me tonight, but I just want to go ahead and, before I give you the first practice problem, talk to you about the shape of the Earth. It is not an exact sphere, but it's so close that we use these formulas when we talk about the Earth. So just so you know, we scientists know it's not an exact sphere, but mathematicians need something, so we use these formulas. So good luck, and I will see you in class.